Have you ever looked at something, really looked, and realized there's more to it than meets the eye? Well, today we're going to be detectives because we're about to uncover the secret geometry hidden in all the stuff we see every day. Let's get into it.
Take this tanker truck. You see these things on the road all the time, right? And at first glance, you just think, truck. But if you look closer, it's not just one simple shape, is it? It's actually a bunch of familiar shapes all stuck together in a pretty clever way.
So, here's the big question. How would you actually measure something like this? Let's say you needed to paint it. How much paint would you need? Or how much liquid could it actually hold? It's not just a cylinder, and it's not a sphere. It's a mix. And that right there is the mystery we're going to solve.
Okay, so our very first clue in cracking this case is all about learning to see things differently. We have to train our eyes to look past the complex objects and spot the simple, basic shapes hiding inside. Think about that tanker again. It's really just a cylinder, a long tube with half of a sphere, a hemisphere, slapped on each end. And once you start looking for it, you see this pattern everywhere. A toy top, a medicine capsule, even some buildings. They're all just combinations of basic geometric solids. And once you can see those pieces, well, that's the first step to measuring the whole thing.
All right, let's tackle the first challenge, figuring out the surface area. Now, this is where things get really interesting, maybe even a little counterintuitive. We're going to call this part the painting puzzle.
The easiest way, honestly, to think about surface area is just to imagine you've got a paintbrush in your hand. The surface area is every single spot on that object that your brush can touch. It's the outer skin, the whole exposed shell of the shape. So look at this toy top. You can see it's a cone sitting on top of a hemisphere. If you were going to paint it, you'd cover the curved part of the hemisphere and the slanted part of the cone. Seems simple enough, right? But how do you get the exact number? How do you actually calculate that? And here it is. This is the aha moment. Imagine the two pieces are separate. The cone has a flat circular base, and the hemisphere has a flat circular top. But what happens when you glue them together? Those flat circles press up against each other, and poof, they're gone. They're on the inside now.
This right here is the whole secret to the painting puzzle. The surfaces that get joined together are now hidden. You can't see them, you can't touch them, so you can't paint them. And that means, this is crucial, you can't just add the total surface area of the cone to the total surface area of the hemisphere. That would be wrong, because you'd be counting those two hidden circles that don't really exist on the outside anymore.
So, to get around this, we need a special tool. It's called the curved surface area, or CSA. It's exactly what it sounds like. It's the measurement of only the curvy parts of a shape, completely ignoring any flat bases. So for our toy top, all we need to do is add the CSA of the cone and the CSA of the hemisphere. That's it. So let's just recap the method. To find the total surface area of a combined object, you identify the individual shapes, you add up the curved surface areas of all the parts you can actually see, and then you add the area of any flat surfaces that are still exposed on the outside, but you absolutely do not add the areas that got stuck together on the inside.
Okay, let's put this to the test with another one. Here we have a decorative block. It's a cube with a little dome, a hemisphere right on top. How would we find the surface area for this thing?
Let's walk through it. You'd start with the total surface area of the whole cube, all 6 sides. But hang on, the spot where that little dome is sitting covers up a circle on the top of the cube, so we have to subtract that circular area. Then we add on the new surface that we just created, which is the curved area of the dome. So it's the total area of the cube minus the covered up circle plus the curved area of the hemisphere. All right, we've totally cracked the painting puzzle. Case closed. But that's only half the story. What about the other part of the mystery? How much stuff can these things hold? For that, we need a whole new approach, and we'll call this one the filling formula.
And here's some really good news. Calculating volume is so much easier. It's way more straightforward. With surface area, we saw how parts of the shapes vanished when we joined them. But with volume, nothing vanishes. The total space is simply the space of one part plus the space of the other part.
So, if surface area is all about painting the outside, volume is all about filling the inside. Just imagine pouring water into the object until it is completely full. The total amount of water you poured in, that's its volume.
For instance, let's look at this industrial shed. It's pretty easy to see that it's a rectangular box on the bottom with a half cylinder for a roof. So to find out how much air this whole shed can hold, what do you think we do? Exactly. You just find the volume of the boxy part, then you find the volume of the half-cylinder roof, and you just add them together. No tricks, no vanishing parts, no subtractions. For volume, it's just a simple sum of its parts.
Okay, now that you're an expert, let's look at one final and really fascinating case study. Because sometimes understanding volume can actually save you from being a little bit deceived.
Check out this juice glass. If you were to measure its height and its width and do the math for a cylinder, you'd calculate its capacity at about 196 cubic centimeters. It seems like a perfectly normal glass.
But is it really that simple? Take a really close look at the bottom of the glass. Do you see it? There's a little trick built right into the design.
The actual capacity is way less. So why is that? Well, it's because the bottom of the glass has this raised hemisphere that pushes up into the drink, taking up space. So the actual volume you can pour into it is the volume of the whole cylinder minus the volume of that hidden hemisphere. A pretty clever, if not sneaky, design. So there we have it. Case cracked. We now have two really powerful tools. For surface area, we solved the painting puzzle. We only add up the parts we can actually see. And for volume, we use the filling formula. We just add the volumes of all the component parts together. Simple as that.
From now on, you have a new kind of vision. You can look at the world around you and see the simple shapes hidden inside the complex ones. A water bottle, a street lamp, the building across the street. You can see them for what they really are. So my final question to you is, what's the first thing you're going to measure? What geometric secrets are waiting right there for you to uncover?